So we have defined the extremal number, and then we show that the extremal number of click, we determine them using the theorem. And next, we want to consider external numbers of more general graph. So not necessarily complete graph, and what would be their external number. So we have this theorem by Erdos Stone Simonovits theorem. So Erdos Stone, 1946. Erdos Simonovits, 1966. This was, essentially the theorem, but the implication of the proof was later written in here. So it's called the Erdos Stone Simonovits theorem. So let's say I have the graph satisfying its chromatic number. Oh my God. Is specified as r plus 1. For given positive delta, and let's use h instead of f. And no, let's use f. F is better. So f is given, and for given delta and f, we have this. So there exists certain number and 0 such that the following holds. For whole n and less than 0. So for large n, the extremal number of n f is at most 1 minus 1 over r plus delta times n squared over 2. So this asymptotically determines the extremal number for large n. Why? We know that this Turan graph, an R-type Turan graph, it says what? Its number of edges is, you can compute it, that's, let's say at least maybe let's subtract a bit. But depending on whether R divides N or not, the exact number computation you can do, but it's almost it. Then, what? This and this, as n goes to infinity, the constant here should be 1 minus 1 over r. You can take delta as large, as small as possible. And, okay, and this does not contain f, because this is r chromatic graph, and this is r plus 1 chromatic graph. So it has no f, and that has at least this many edges. So that provides a lower bound of this extremal number, which is t sub rn. So this theorem determines the asymptotic of this extremal number. So we want to prove this. Then that provides an understanding of this extremal number. So what's the basic idea? So if chromatic number is r plus 1, that means f is subgraph of large complete R-type graph. So what we have to prove, if we have a graph G with more than this many edges, And what we will prove is that it had a subgraph. It had a subgraph isomorphic to this large complete alpha type graph that automatically contains X, so that provides an upper bound. For that, we first prove this claim is that which basically says that here we have a, we will assume that she has many edges, but the edges more than this many edges. But instead of that, if we have a minimum degree condition, then we can find the large complete alpha type graph. So that's what this claim is saying there. So meaning, so for given R, H, and delta, there exists the N1, which is depending on the R, H, delta, such that the following holds. For N bigger than N1, bigger than or equal to N1. Okay. But that if the G prime is an M vertex graph with a minimum degree bigger than or minus 1 over R plus a delta over 2. And then if G prime contains a complete R plus 1 part type graph with each part having size at least H as a subgraph. So essentially, this claims that if we have a minimum degree condition instead of the number of edge conditions, then we can do what we want. Okay. So let's prove this claim. So what we do, we use induction on R. Okay, so if R is 0, then what? Just when R is 0, what you want to find is just the set of H vertices. So this is one part type graph, no edges at all. Then just letting this N1 be as R, H, delta, as H work. As long as there are H vertices, you just take them, and that's what you want. So assume if R is at least 1, and we will show that if N1 R, H, delta, we can take it as a N1 of R minus 1 T delta. So this exists from the induction hypothesis times T times T to the H to the R would work, where T is defined as, say, 4H divided by delta, taking shielding. So this is what we will show. This is induction step. So, okay. So let this N1 be N1 times R minus 1 T delta T times T to H to the R. Then what? Then, because this is bigger than this, induction hypothesis gives, so notice that you have T here instead of H. And because R is smaller by induction, this exists. This gives complete R part type graph. The subgraph with, say, part type sets A1 to AR of size T. Let U be the vertices outside of this AI, A1 to AI. And let U prime with the vertices in U such that it has, in this G prime, it has many neighbors in each of AI, at least H many, for all I. So you have A1, A2, A3. Then outside, if some vertex has at least H neighbor, at least H neighbor, at least H neighbor, then that's in U, right? And there are already these are complete are particular. So now what we want to show? We want to show that this U prime. We want to show that this U prime is not too small. To show that for each U in U prime, let's define it for U. For each U, for any U's here, we define W sub U as the tuple of vertices, where the last tuple is U. That is, each VI is the neighbor of U in the G prime, and then it's also in AI. For each, right? So if this has this neighbor, and you take this, that's tuple of 4 vertices, which lie in W. You do that for other choice. This comma, this is also there. This comma, this is also there, and so on. So you get many of them. Then what happens? For each vertex U, which is in U but not U prime, what happens? Such a vertex, there is certain I that its number of neighbors there is strictly more than H. Then what? We have that in this tuple, one of the choices has less than H choices, and then other thing is at most T choices. Because each AI has size T. Then its size is H times, at most H times T to the R minus 1. Then what do you have? Letting W be the union of all W or all U, vertex U in U, you know that this entire set has size at most what? For each U prime, for each vertex in U prime, it's WU has size at most P to the R. So that's maximum possible size. And in this or the tuple in here, the last digit, even if the first digits are the same, last digits are different for each vertex. This summation covers every possibility. So for all U which does not lie in U prime, it's outbounded by H times T to the R minus 1. This is at most what? T to the R times U prime plus the remaining one is at most N times H T R minus 1. So you have this. So you have this inequality. On the other hand, what? You have a U prime here. Now we want to find the roll bound of W. Then you can move this to here and then you divide to get the roll bound on U prime. So we want to obtain roll bound on this W. For each, though, we have defined this, and then this count is based on the choice of U. For fixed U, and you find upper bound, and then you get that. Now we count in a different perspective. For each this tuple, we want to count U. For each tuple, we want to be R in A1 plus AR, what we have is that we consider the common intersection of neighborhood of this. So how did we choose it? This is that U is adjacent to all of them. In other words, this U lies inside of the common neighborhood of this. So you consider its common neighborhood. Then that provides a number of choices of U. That's what. If you have this, and then you have neighborhood, 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 then this common neighborhood size is what? For the entire set, you delete the size of non-neighborhood of the first set, and you delete the non-neighborhood of size of the second set, and you delete the non-neighborhood of the third set. You keep subtracting it, and you get the lower bound on the size of it. Right? So from the entire set, you subtract the size of the non-neighborhood of that, and due to its minimum degree condition, the non-neighborhood size is at most smaller than this. Degree minus 1, because this degree plus plus 1, sorry. Wait, minus 1. Degree plus non-degree should be summed to n minus 1. So you have this. So what? So lower bound is that you add this r times, and each of them is this. Then what you get is r delta and half times r delta. So then what we have, the W is at least you consider all possible tuple. You add the number of choices of U. So for this, how many U's can you put on the last side? It's at least this many. Then what? This is half times R delta T to the R, so number of choices here. And now what? You have this upper bound, and then this upper bound on W and this lower bound. Then what do we get? T to the R U prime plus M H T to the R minus 1. U prime is what? You have this, but the T was chosen in this way, so this one is smaller than 1/4 delta n. So this is at least 1/4 r delta n. Okay. So now we know that the U prime is large. What do we have now? We have A1, A2, A3, and you have U prime, which is large. So for each U in U prime, we consider, so U prime has at least H neighbors, at least H neighbor, at least H neighbor. We consider a tuple. Okay, you choose a tuple. For each U, you choose a tuple so that, say, P1 U, that P R U, such that its PRU is set of neighbors of U in AI, and its size is H. So you might have a neighborhood bigger than H, then you arbitrarily choose H vertex, and then let it be your P3U. In the same way, you choose 1, 1, 1. So there are more than one choices, but you fix arbitrary choice. Okay, now, but then for many of them, we did this. And then there are a fixed number of choices for this, right? So by Pigeonhole principle, how many choices possible here? T choose H choices are in each one of them, and then you take the R. So there are that many possible tuples that you get. So by the Pigeonhole principle, there exists a tuple, say V1 to VR, which is in A1 choose H, comma, AR choose H, such that F inverse of V1 to VR has, this is exactly the U, whose F value is exactly chosen to be this, is at least what? U prime divided by T to the H to the R. But U prime is assigned at least 4, 1/4 R delta N, and then N was chosen in this way. Then what? And H is 50. So that's, you just plug that in here, then you can check that this is bigger than H. And that's why we take the N1 to be in such a way. Then, and that's a choice of, for those H vertices you take, and then you take this V1, V2, V3, and dot, and every vertex here is adjacent to every one of them here. And then you know that by induction hypothesis, this is subset of AI. So they already form a complete alpha type graph. So such a choice of disjoint vertex sets V1 to VR and F inverse of V1 to VR form a complete R plus 1 type graph. With each part having size H, and this proves the claim. So with this claim, we can prove the theorem, Erdos Stone Simonovits theorem. So let H be the number of vertices in H. F. Wait, did I use F for H? F, yeah. And let N0 be the 4 delta inverse times N1 RH delta. Assuming N is bigger than N0, and E is an N vertex graph with at least 1 minus 1 over R plus delta times N squared over 2 edges. Then, by a well-known fact that there exists a subgraph G prime of G with the number of vertices, let's say N prime, satisfy that it's at least delta N over 4, which is N1 R H delta with its lift this, and its minimum degree is at least 1 minus 1 over R plus delta over 2 N prime. So this exists. You can actually prove this. This is not too difficult exercise. Basically, you have a G, and if G has, let's say, N vertices, let's say that's, N vertices, and then if it has if it satisfies this condition with N prime being equal to N, that's great. Otherwise, you have a vertex with 2 row degree, you delete that. And in the remaining graph, you see again. So this have again too many, does it have a vertex with small degree? And while you're doing that, now you adjust that the n-1 is your new n prime. With that choice, is there another new vertex which has too small degree, then you delete. You keep do that. While you're doing that, you delete it only when this is, only when the degree is smaller than this. And then here, this was delta over 2, while you have delta edges. So there is gap. So every time you delete, the number of edges adjusted to here are not really sufficiently large. It's a bit smaller here. Then you can actually show that this process stops at some point, and then it stops at the point with more than this many vertices remain. Otherwise, you can get a contradiction that the graph has too little number of edges, little smaller than that. So that's basically proof idea. And you need to do some computation, but it's possible. And from this fact, we use this claim, this G prime contains a copy of complete R plus 1 part-type graph, where each part has size f, that contains f as a subgraph, because f at f is a R plus 1 chromatic graph with h vertices, so it's a subgraph of this. So that proves the theorem. Okay, so this Erdos Stone Simonovits theorem provides the asymptotic value of this extreme number. So it seems that it gives a satisfying answer for any graph f. But if you think about it, if R is 1, so if S is bipartite graph, and this is 0, then this just says that the extreme number is just subquadratic, or arbitrary delta is smaller than this. But it doesn't specify how fast it grows. So in that case, it doesn't really give you the asymptotic. It's just saying it's subquadratic. It doesn't say whether this is linear or this is some constant times 1 to the 3 over 2. It doesn't distinguish those cases. Or some constant times into the 3 over quarter. That's too small, say 4 over 3. Or linear, it doesn't distinguish those. So this gives us a satisfying answer for graph f, which is not bipartite. For bipartite graph, we need to, do more work to get more results. And mostly we don't know much about the extreme number of bipartite graph. Only sporadic cases are known. And we will talk about that in the next video. Okay, thanks for listening. I will see you in next video.